everyone. Muriel Medard here, CEO, co-founder of Optimum. I'd love to talk to you today about quantum computing or post-quantum or PQ. A lot of people talk about quantum computing as though it were something magical, mystical, but we'll see it's just math. And the math is creating the problem. Fortunately, it's also the math that's going to create the solution. So let's start with what is quantum computing. So normally we think of bits, and bits can take two values, 0 or 1. Quantum computing has something slightly different, which is called qubits. And qubits might not be only able to take the values 0 or 1. They instead have something probabilistic, non-deterministic, which is effectively like a distribution between these zeros and ones. So think of traditional computing as being a degenerate extreme case of a qubit where the distribution is absolutely not in any way rich or ambiguous. Okay, so this non-determinism in quantum computing turns out is extremely powerful. And that's why people get so worried about what this power of quantum computing might actually come and do relative to the cryptographic techniques that we have out there and which are securing so much of our data, our lives, and our livelihoods. So it turns out that quantum computing has a very difficult set of challenges. And the main set of challenges is that these 0 ones with a distribution, so I'm going to call it something in between, don't stay constant. In particular, they degrade. They degrade in time, and they're sort of really difficult to capture and to preserve. One of the ways that people try to get around this is, for instance, operating at very low temperatures to slow down that degradation. Another way that people try to manage it is to create mathematical structures that do error control. So error control coding is a type of mathematical operations that allow this degradation to be managed as much as possible. And therefore, a lot of the research that's going on right now in quantum computing is on this error correction through error control coding. So it's kind of math coming to the rescue of some really difficult physics problems. All right, so effectively, quantum computing to a large extent is going to be managed through coding, where coding, as we've discussed before in some of our previous sessions at the board, is the mathematical representation of data for robustness, speed, and other desirable properties. All right, so coding is actually creating part of the problem that we have right now with the PQ world. It's going to make it more powerful. As I mentioned before, math is creating the problem. Math is also going to come and help us fix the problem. And let's see a little bit what that problem is. So if you think of security as a door, like you would have for your house, what you want is a door that you can open, that you can access the house, but also a door that is robust to somebody else. And so if you think of the door, the way we generally think of managing the security is through basically having the security as a key. So I have a key here, and this key is going to open my door. And a natural thing for us to do is to think of securing keys. As a matter of fact, it's exactly the same terminology that we use for a physical door as what we use in security when we're talking about a key. So what a lot of the systems right now that purport or that seek to be PQ secure are doing is they're actually trying to make this locking key a more secure locking key. So maybe you're making this key more difficult to replicate. Just like you would with a physical key, if you're worried about security, you might try to make that physical key more difficult to replicate. Maybe people have, say, a 128-bit key, and now they're going to a 256-bit key. So you have systems which are basically around key management, and those systems that are around key management are trying to beat the possible capabilities of a quantum computer. That's great. But once you have a quantum computer, remember these quantum computers are non-deterministic. It doesn't necessarily mean that somebody can go and pick a particular person's lock and get in. What they can do is they can go around and probabilistically test all kinds of things that they might break. What that means is you might actually have somebody trying to punch places in different parts of your door. And once they've punched into the parts of the door that somehow were more fragile, which you might not have known were particularly fragile until somebody really was testing and pressing on them, now they actually can see through the door, or of course they can reach in maybe and unlock from the inside. So now what you have is not just the key that you need to worry about, but the entire door. Now, it turns out that the systems that are robust to post-quantum attacks have been known for a long time, really since the 1970s. So let's go back to the 1970s and let's look in particular at the work of the late, great Bob McEliece, information theorist of great note. And he created a system which is based on coding, just like the error control coding. Actually, it's very related to error control coding. He created a system based on coding, which has stood the test of time in terms of what people think they can do once they have quantum computing more widely available. So from the 1970s, we have actually known how to secure against any sort of PQ type of environment. Question. We've known how to do it for ages. Why are we not doing it? Why are we so worried? Why do we have this vision that PQ is going to be some calamitous Armageddon of, security failures? Well, it's because this is actually really, really hard to do. It's really expensive. Sometimes I compare it, unfortunately it's a sad comparison, to something like chemo where, you're killing the tumor, but you're almost killing the patient. It's really, really hard to manage and actually apply a McEliece cryptosystem. It takes a lot of time, takes a lot of energy, takes a lot of bandwidth, takes a lot of storage. It's really expensive. Okay, so because of that, people say, well, it's so expensive, I'm only going to do it on the key, and I'm going to worry about the key. Now, by all means, one should worry about the key on the door. There's no question about it. But the key is not the entire door. What matters if somebody is able or not to break into my lock if they made a hole in the door? The problem is the hole in the door. So McEliece is expensive. There are other systems, by the way, out there. I'm taking McEliece just as, the earliest sort of more sturdy standard representative, but there's a wide variety of schemes, all sharing that really expensive characteristic with respect to deployment. Now, let's think of what we can do with respect to the door. Well, I could apply McEliece, but it'd basically be like saying, you know what, I've got a solution for you. You are going to have a door which is just massive stainless steel. And it's going to be, half a foot thick. And people are not going to be able to make a hole in it. And you go, that's great, but that's really heavy, that's really expensive, and I just can't afford it. I can't, even open it every day. It's so heavy. The idea with coding, and this is something that with collaborators in my group at MIT we've co-developed, is to use something called HUNCC, which is basically a universal system using network coding. And the idea is the following. What I'm going to do is again use coding, because remember, coding is the core technique that we're using to make quantum computing a reality and also to protect against this reality of quantum computing. What we're going to do is we're going to have multiple pieces of data, say X, Y, Z, and instead of trying to protect X and protect Y and protect Z, which would be like protecting the entire door with this heavy-duty, half-a-foot thick stainless steel type of armature, what we're going to do is instead we're going to turn this into three equations, say 3x plus 2y plus z, and maybe 7x plus y plus 11z, and something else, maybe 8x plus 5y plus 19z. And now we have these three equations. I'm going to only encrypt with one of these heavy-duty schemes, say McEliece. I'm only going to encrypt one of them. So in this example, I only had to expand the encryption cost to 1/3 of the data. Now here I only wanted to put three equations because I don't want to have to write a whole lot. But imagine that I could do this to 1/10 or 1/20 or 100th of the data. Basically a small fraction of the data. And what this does is that it protects the entire data by encrypting, by bearing the cost of encryption only on a fraction of the data. It's as though now you were putting a thin layer of metal that is enough in any one location to prevent punching through and is able to protect the entire door. So now you cannot punch through the door, because to punch through the door, you would have had to punch through a specific point of the door. And remember that the aspect here that's very important is that, you know, you're just trying to find the weakest link. Now, basically, you have replaced that with the fact that, you know, in order to be able to break this, they have to break the entire thing. They have to specifically break that piece, okay? Otherwise, they are no more wise about the information than if they had seen nothing else. So basically, that's it. That's how we're using coding, both to facilitate quantum computation and also protect against quantum computation. I hope you've enjoyed this.